In the vastness of space, some 650 light-years from our planet, a cosmic clock is counting down. This ticking time bomb, when it finally erupts, will send a wave of searing radiation and superheated matter racing through the Milky Way, obliterating anything unfortunate enough to be in its direct path. Worlds orbiting too closely will be torn apart, their rocky surfaces melted into oceans of lava, their protective atmospheres blasted away into the void. And this impending cataclysm is close enough that you can see it with your own eyes on a clear night. It's one of the brightest points of light in the heavens. It is Betelgeuse, the closest red supergiant to Earth, and it is destined to explode in a supernova. But when will this happen? In centuries, years, or perhaps even days? And what would such an event mean for life on our planet? To find answers, astronomers have been studying this unstable giant as it balances on the edge of destruction, trying to decode the signals that might warn of its final act. And as the countdown continues, the star keeps surprising us. Let's begin with the fundamentals. Betelgeuse ranks as the 10th brightest star in our night sky, easily spotted as the left shoulder in the constellation Orion. If you look for it, you'll notice it has a distinct reddish hue compared to nearby stars, and it twinkles noticeably. That red color is a hallmark of its classification. Betelgeuse is a red supergiant, a type of medium-mass star that has swollen to an enormous size. It dwarfs our own Sun, with a radius so vast it would extend beyond the orbit of Mars if placed in our solar system. Betelgeuse is nearly 900 times wider than the Sun, yet it may only be about 10 times more massive. This means its material is spread incredibly thin, resulting in very weak surface gravity, so weak that it can barely hold onto its own outer layers. This is why scientists observe massive convection cells, like giant bubbles, churning on its surface in simulations. Imagine witnessing a sunset from the surface of such a star. Of course, the most captivating detail about Betelgeuse is its inevitable end. Supernova explosions within our own galaxy are rare events, while telescopes detect hundreds of them in distant galaxies each year, a testament to the sheer number of galaxies in the universe. Within the Milky Way, we likely witness only 2 or 3 per century. So the odds of one happening tomorrow are low, but not zero. What would be the consequences of such a blast? The impact depends entirely on distance. Intriguingly, geological evidence suggests Earth has felt the effects of supernovae in the distant past. Our solar system resides in a region known as the local bubble, a cavity in interstellar space about 1,000 light-years across. This bubble is believed to have been carved out by a supernova explosion between 10 and 20 million years ago, an event our planet would have experienced. Scientists have also identified evidence of a supernova that occurred roughly 2.5 million years ago, found in a specific layer of Earth's crust enriched with rare isotopes like iron-60 and manganese-53. This explosion was far enough away to cause no harm. However, some researchers theorize that a much closer event might have played a role in the extinction of woolly mammoths around 13,000 years ago. Potential impact sites from that era contain magnetic spherules and radioactive potassium-40, substances commonly found in supernova debris. Even earlier, mammoth tusks dating back 34,000 years have been found pitted with tiny craters from grains of slightly radioactive iron traveling at speeds around 10,000 kilometers per second, a velocity typical of material ejected from a supernova. That couldn't have been pleasant for the creatures involved. This dive into the geological record offers a fascinating window into our planet's history. From these clues, an important fact emerges. 7 billion years ago, and we've experienced a handful of supernova effects in the last 20 million years with life persisting. Apologies to the mammoths. Then these stellar explosions aren't universally apocalyptic. The key, as mentioned, is proximity. A nuclear detonation 1,000 kilometers away is a distant concern. One on your desk is a catastrophe. In cosmic terms, the universe has very large desks. To grasp the sheer power of a supernova, we must understand the forces at play. This means looking at how stars like Betelgeuse reach their explosive end. There are two primary paths to a supernova, each requiring a specific type of star. The first path leads to a type Ia supernova. This typically involves a white dwarf star in a binary system. The white dwarf slowly steals matter from its companion star until it reaches a critical mass threshold. The process isn't fully understood, but it's believed the white dwarf, a dense stellar remnant with a core of carbon, like a gigantic cosmic diamond, exists in a delicate balance. Two opposing forces are at war: electron degeneracy pressure and gravity. Electron degeneracy pressure is a quantum mechanical effect where electrons resist being compressed too closely together. Gravity, however, is relentless, constantly trying to crush matter inward, especially in an object as dense as a white dwarf, where a sugar cube-sized piece can weigh as much as a car. In a binary system where the white dwarf is feeding, gravity eventually wins. It overwhelms the electron pressure, causing a catastrophic collapse. Carbon fusion ignites almost instantaneously across the star. Within seconds, most of the star undergoes nuclear fusion, creating heavier elements and releasing an unimaginable amount of energy as the star rearranges itself into a more stable state. How much energy? Approximately 1 quatuordecillion joules. That's a 1 followed by 45 zeros. This colossal energy is released in a matter of seconds, violently ejecting the star's entire contents in all directions at about 6% the speed of light. A flood of gamma radiation also floods outward. For a few weeks, the supernova shines with a brilliance 5 billion times greater than our sun, fading only as the expanding debris cloud dissipates. The second type, a type II supernova, is more relevant to Betelgeuse. This involves a massive star, at least 5 times heavier than the sun, reaching the end of its life. These stars are still actively burning fuel. An internal balance is maintained by the outward pressure from fusion reactions in the core, which convert hydrogen into helium, fighting against the inward pull of gravity. Eventually, the hydrogen fuel in the core is exhausted, converted to helium. Fusion halts and gravity gains the upper hand. The core compresses. If the star is massive enough, this compression heats the core until it's hot enough to begin fusing helium into heavier elements like carbon. This cycle repeats for elements like oxygen and neon. With each new fusion cycle, the star's internal pressure causes its outer layers to expand further. It enters the red supergiant phase, like Betelgeuse, while its core is progressively converted into iron. Here lies the ultimate problem. Red supergiants cannot fuse iron into heavier elements. Iron fusion consumes energy instead of releasing it. So, when the core becomes mostly iron, fusion stops entirely. Without that outward energy from fusion, even electron degeneracy pressure cannot support the star's immense weight against gravity. The core collapses catastrophically, similar to a type Ia event, but with a crucial difference. In a massive star supernova, part of the core often remains behind, collapsing into an ultradense neutron star or a black hole. A white dwarf in a type Ia supernova is typically completely destroyed. The scale of material and energy released in either type of supernova is staggering. Anything in the immediate vicinity is doomed. This is energy powerful enough to tear apart a star. A planet would stand no chance. Thankfully, our sun will never go supernova. It's not massive enough. But if it did, Earth would likely be partially or completely vaporized. Its rocky surface would boil under temperatures 15 times hotter than the sun's surface, and the planet would be swept away in the supernova's expanding shockwave over several weeks. Surprisingly, this initial wave of destruction fades quickly with distance. In fact, being vaporized isn't even the greatest threat a supernova poses to a planet. In 2011, researchers from the University of Cambridge calculated that planets orbiting as close as 15 billion kilometers from their star, about 100 times the Earth-Sun distance, would survive the blast physically intact. They would simply be flung into interstellar space, now orphaned and without a sun to orbit. Any hypothetical ecosystem on such a world would face other dire problems, like freezing temperatures almost immediately. Even if a planet's crust remains, life on its surface would be unsustainable. The flash of a supernova can outshine an entire galaxy, potentially blinding any creature that looked directly at it. More critically, high-energy radiation would strip away and chemically alter a planet's atmosphere. It would destroy the protective ozone layer, dramatically increase radiation poisoning risks, and kill foundational organisms like ocean phytoplankton. This would trigger a mass extinction event as the effects cascaded up the food chain. Scientists estimate this kill zone extends to about 25 light-years from the supernova. Beyond that distance, the fury of the explosion diminishes. While the mammoth-affecting debris potentially came from a supernova 250 light-years away, that was likely an unlucky strike. Generally, at 250 light-years, we wouldn't notice significant damage. The radiation levels wouldn't be high enough to cause mass extinctions. By 500 light-years away, the event would be little more than a spectacularly bright new star in the sky for a while. So you can breathe a sigh of relief. Betelgeuse poses no imminent threat. Are there any other supernova candidates within 300 light-years we should worry about? Scientists are fairly confident the answer is no. Massive stars are easy to spot, and the only two nearing the end of their lives, Betelgeuse and Antares, are both over 400 light-years away. White dwarfs are trickier due to their faintness, making them harder to catalog and assess for risk. However, in 2013, data from the European Space Agency's Gaia Observatory helped identify about 13,000 white dwarf stars within 326 light-years of Earth. Despite this large number, researchers are confident none are poised to explode anytime soon, with soon meaning within the next several 100,000 years. So, for now, we are safe from a nearby supernova. When Betelgeuse does explode, Earth will be unharmed. The shockwave would take centuries to reach us, and by then, its force would be weaker than the solar wind. Our protection wouldn't come from Earth's magnetosphere or atmosphere alone, but from the sun's own heliosphere, the vast bubble of charged particles surrounding our solar system, which would deflect and absorb the incoming material. No harm will come to Earth, but the event will be an incredible spectacle. Betelgeuse could shine as brightly as a full moon, potentially visible even during the daytime. Just imagine that for a moment. Witnessing a supernova in our sky would be a historic event for humanity and could unlock many secrets about these powerful explosions. This is why Betelgeuse holds such fascination, much of it centered on that one burning question: when will it happen? Betelgeuse will explode soon in astronomical terms, which could mean anything up to 100,000 years from now. However, some scientists, based on estimates of a larger-than-expected radius for the star, speculate it could happen within the next few decades. This raises the tantalizing possibility of witnessing a local supernova within our lifetimes. But Betelgeuse guards its secrets closely and has thrown many surprises at astronomers over the years. The inner workings of such stars are complex. Betelgeuse dims and brightens according to several overlapping cycles that aren't fully understood. It has a fundamental rhythm likely tied to its eventual explosion, along with several overtone cycles. These cycles range from a few hundred days to 2170 days, and there's debate over which is the primary one. This complexity means something interesting always seems to be happening with Betelgeuse. It made headlines in 2009 when it appeared to shrink by 15%. Then, in late 2019, it underwent the Great Dimming, its brightness dropping dramatically. Speculation ran wild that this was a prelude to the supernova, but that was likely not the case. Data from the Hubble Space Telescope suggested the star itself wasn't dimming significantly. Instead, a cloud of dust was to blame. In September 2019, Hubble observed hot material being ejected from Betelgeuse's atmosphere. In the following months, this material cooled as it moved away from the star. By December, it had drifted in front of our line of sight, obscuring the star's southern hemisphere and causing the dimming. At its peak, Betelgeuse was about 2/3 dimmer than usual. By April 2020, it had returned to normal brightness as the dust cloud moved or dispersed. This event, however, sparked renewed scientific interest, leading to an incredible discovery. While Betelgeuse dims and brightens in various cycles, not all are caused by dust. At least one long cycle might be the work of a tiny companion star. For over a century, scientists had wondered if Betelgeuse was part of a binary system. Proving it was a huge challenge because the star's surface is so turbulent, making it hard to detect the subtle dimming caused by a companion passing in front. After the Great Dimming, two independent research teams, one from the Harvard-Smithsonian Center for Astrophysics and another from the Flatiron Institute Center for Computational Astrophysics, found compelling evidence. They analyzed historical data on Betelgeuse's motion and brightness and noticed a tiny, repeating wobble every 2170 days, as if being tugged by an unseen object. This wobble coincided with periods of dimming. Both teams believe the companion, nicknamed Betelgeuse, officially designated Siwarha, has a mass similar to our Sun and orbits Betelgeuse at a distance slightly less than that between our Sun and Saturn. 1-meter mirror and a special high-resolution camera to search for the faint companion when it was predicted to be at its farthest point from the giant star. They found a blurred but promising image of a very dim object right at the limit of the telescope's resolution, believed to be Siwarha. While not 100% confirmed, other observations align with this finding, making it highly likely. A definitive check will come around 2027 when the companion is next at its greatest separation. If confirmed, this is a fascinating new chapter in the star's story. It also helps astronomers rule out the 2170-day cycle as the fundamental mode that dictates the supernova's timing. This makes it more likely that Betelgeuse's explosion is further in the future, perhaps not in our lifetimes. While disappointing for hopeful skywatchers, it's probably a relief for Betelgeuse, which will be well within the destructive radius when Betelgeuse finally goes supernova. Predicting the exact moment remains difficult, partly because Betelgeuse behaves in confusing ways. For instance, observations from the ALMA telescope array suggested Betelgeuse is rotating at a breakneck speed, completing one full rotation roughly every 20 years. That might sound slow, but for a star of its colossal size, it means the surface is moving at about 5 kilometers per second, or 18,000 kilometers per hour. That's 10 times faster than the rotational velocity we experience on Earth's surface, and seems to defy the expected physics for a star of its mass and size. How do we measure the spin of such a distant, blurry object? Astronomers use a clever technique based on the Doppler effect, the same phenomenon that makes a siren's pitch change as an ambulance passes by. When a star rotates, one side of its surface moves toward us, and the other side moves away. Light from the side moving toward us is shifted slightly toward the blue end of the spectrum, blue shifted, while light from the receding side is shifted toward red, red shifted. By measuring this color gradient across the star's blurry disk, scientists can calculate its rotational speed. This is how ALMA data suggested the 5 km/s speed. The problem is, basic physics says a star as large and massive as Betelgeuse should spin much more slowly. If our Sun were expanded to Betelgeuse's size, its rotation would slow to a crawl to conserve angular momentum, just like a spinning ice skater slows down when they extend their arms. One theory to explain the fast spin is stellar cannibalism. Betelgeuse might have consumed a companion star in the past, absorbing its angular momentum and spinning up in the process. However, a recent international study proposed a startling alternative. Betelgeuse might not be rotating that fast at all. The observed color gradient could be a giant optical illusion. Betelgeuse's surface is a turbulent, boiling cauldron of massive convection cells. Bubbles of hot gas larger than 100 million kilometers across that rise and fall at speeds up to 30 km/s. This creates a chaotic patchwork of areas moving toward and away from us, each producing their own small blue shifts and red shifts. When viewed from 650 light-years away with limited telescope resolution, this random patchwork of colors can be misinterpreted as the smooth, organized gradient produced by rotation. Simulations suggest that about 90% of the time, Observations of such a turbulent surface would be mistaken for fast rotation. This means astronomers now have a key goal: obtaining higher resolution observations of Betelgeuse to distinguish between true rotation and surface turbulence. Better images already exist but require extensive analysis, which will take time. The answers are on the horizon. So there you have it, a comprehensive look at Betelgeuse, a star teetering on the edge of a cosmic cataclysm. It's no wonder we are captivated by such a violent event. Humanity has always been drawn to explosions, as evidenced by our love of fireworks. Whenever it arrives, the supernova of Betelgeuse will be an awe-inspiring sight in the night sky. And we can all be thankful that, in this case, we'll have the best seat in the house from a very safe distance. If you enjoyed this journey to the brink of a stellar explosion, make sure to subscribe for more explorations into the wonders of our universe. Give this video a like if you found it fascinating, and share it with anyone who gazes up at the stars and wonders what's out there verse. Give this video a like if you found it fascinating, and share it with anyone who gazes up at the stars and wonders what's out there.